Greetings and welcome to the Singapore Math Olympiad 2024 Junior Section Round 1 walkthrough for the first 15 questions of this morning's Olympiad. In question 1, we're given the quadratic equation x squared plus 4x plus 16 equals to 0 and we want the value of x cubed. Pause the video here and give this question a good try. So what we could do is we can take the quadratic equation and we'll multiply all the terms by x. This will give us a cubic x cubed plus 4x squared plus 16x equals to 0. Now we bring the 4x squared plus 16x over to the right hand side. This will get us x cubed equals to negative 4x squared minus 16x. We're able to factorize out negative 4 and this will give us a factor of x squared plus 4x. Which we can find from the original equation, x squared plus 4x is equals to negative 16. So we'll replace it here, and this will give us the answer, x cubed is equals to 64. In question 2, we'll let a be a real number between negative 1 and 0. Basically, we want to order pi to the power of a, 1 over pi, and 1 over pi to the power of a. So we'll arrange them in ascending order. Pause the video here and give this question a good try. So for convenience, we're going to just assume that a is equals to negative 0.5. This will help us draw the 3 power graphs that we need to solve this. So the 3 power graphs we need is firstly shown in green, y equals to square root x. Next we have y equals to 1 over x shown in red, and y equals to 1 over square root x shown in blue. These 3 graphs all pass through the point 1, 1, and after that they split up, and you can see that when x is equals to pi, at this point the green graph is above the red graph, which is above the blue graph, and we sub the value x equals to pi into these 3 curves, we'll get the order of ascendancy, which is pi to the power of negative 0.5 is smaller than 1 over pi, which is smaller than pi to the power of 0.5. This tells us that option A must be the correct one. Question 3. How many non-congruent triangles are there whose sides have integer length and the longest side has length 10 units? Pause the video here and give this question a good try. Okay, so first things first, we need to recall the triangle inequality that the sum of 2 sides have to be greater than the third. So in this case, I'm going to let 2 sides be a and b, and the third side be the longest side, which is 10. So let's look at the various cases. So we're going to construct cases for the various possible shortest length. So by constructing a table, let's assume that the shortest length is 1, 2, 3, 4, 5, and so on. You'll see that if the shortest length is 1, the third side must be 10. It can't be 9 because 1 plus 9 is not greater than 10. So it breaks the triangle inequality. And we can do the same thing for 2. If the shortest length is 2, the third side can only be 10 and 9. If the shortest side is 3, the third side can only be 10, 9, and 8. You see that anything smaller breaks the triangle inequality, and we can continue this for length 4 and length 5. But notice that when we go from length 6 to length 10, the number of possible sides doesn't increase anymore, because let's take the case where the shortest length is 7. The third side can be 10, can be 9, can be 8, can be 7, but it can't be 6 because 6 will be shorter than 7. So in this case, it's just looking at the various cases and adding them all up, you'll see that there are a total of 30 possible non-congruent triangles. So in question 4, we're given a diagram below. The points B and E lie on AF and DF respectively. AE and BD intersect at point C. We are also given a set of equal lengths. AB equals to AC, BD equals to BF, EA equals to EF, and we want the angle BAC. So pause the video here and give this question a good try. Okay, so firstly, we're going to use the fact that BD equals to BF. We can label these 2 base angles of the isosceles triangle as equal, and we'll let them equals to the angle X. Next, notice that angle ABC is the exterior angle of the triangle that we were looking at. Therefore, angle ABC is the sum of the two angles x, which will be 2x. But we're also given the equality that side AB and side AC are equal. So ABC is an isosceles triangle, so angle ACB is also equals to 2x. Next, we haven't used EA equals to EF yet. That will make triangle AEF an isosceles triangle, so angle EAF will also be x. So note triangle ABC. We know the three angles are x, 2x, and 2x. So the sum of these three angles, 5x, must be equals to 180 degrees. Therefore, angle BAC, which is equals to x, is equals to 36 degrees. And that's our final answer. Question 5. Let x, y, and z be real numbers where x cannot be 0, y minus z cannot be 0, z plus x cannot be 0, and we're given 2 over x equals to 4 over y minus z equals to 5 over z plus x, and we want the value of 7x minus y over y plus 2z. So pause the video here and give this question a good try. Firstly, we can equate 2 over x to 5 over z plus x. By simplifying this, we realize that 2z is equals to 3x. And that allows us to simplify the expression that we want and replace the 2z with 3x. So now what we want is 7x minus y over y plus 3x. Now if we equate 2 over x with 4 over y minus z, we can simplify that to give us 4x equals to 2y minus 2z. Now earlier we know that 2z is equals to 3x. So this allows us to simplify. We will replace the 2z with 3x. Then we'll get x in terms of y. So x is equals to 2y over 7. We can put that in our final expression. So we're going to replace 7x with 2y and x with 2y over 7. You'll see that the entire expression is totally in y for the numerator and denominator. That allows us to cancel the y top and bottom, which gives us a fraction of 7 over 13 as our final answer. Question 6. Let n be a two-digit whole number. When 2692 is divided by n, the remainder is 13. When 2978 is divided by n, the remainder is 14. Find the sum of all possible values of n. Pause the video here and give this question a good try. So by subtracting 13 away from 2692, we know that n must divide 2679. Doing the same thing for 2978, we'll subtract 14. We'll know that n must divide the 2964. So n has to be either the highest common factor of these two 4-digit numbers or some factor of that highest common factor. So let's find that highest common factor first. Because the numbers are pretty big, we're going to use the Euclidean algorithm. This tells us that the highest common factor of these 4-digit number is equals to the highest common factor of 2679 and the difference of 2964 and 2679, which is 285. So we can repeat this algorithm. So this highest common factor of 285 and 2679 has to be the highest common factor of 285 and the remainder when 2679 is divided by 285, which is 114. We repeat that again. So now we want the highest common factor of 114 and the remainder when 285 is divided by 114, which is 57. And here you can see that 114 is double of 57. Therefore, the highest common factor is 57, which is 3 times 19. So n can either be 57 or it could also be 19. It cannot be anything smaller because the remainder is already 14. Therefore, we can just sum up these two values of n to get the final answer of 76. Question 7. This is an easy one. X is a positive integer such that 2 to the power x plus 2 to the power 89 equals to 512 to the power of 10. Find the value of x. Pause the video here and give this question a good try. Notice that 512 is 2 to the power of 9, so we can simplify that to 2 to the power of 90 on the right hand side. Note that 2 to the power of 90 is 2 times of 2 to the power of 89, so it's just 2 to the power of 89 plus 2 to the power of 89. Therefore, x is equals to 89. Question 8. The diagram below shows a right-angled triangle ABC. The side AC and AB are in the ratio 3:5. The point D lies on BC such that AD is perpendicular to BC. Furthermore, we are told that DB is 8 cm longer than CD. What is the length of BC? Pause the video here and give this question a good try. So let's label AC to be 3x and AB to be 5x. We can also call CD as y, and BD is 8 cm longer, so it's y plus 8. Now, we can use Pythagoras theorem to work out AD squared, and we can work it out in two different ways by considering triangle ADC and triangle ABD. This gives us two different expressions for AD squared, which is either 3x whole thing squared minus y squared or 5x squared minus y plus 8 squared. We can simplify the two different ways, so we have an equation, so let's simplify that. You'll just see that x squared has to be equals to y plus 4, and this is going to be our first equation. Next, we can consider the big triangle ABC. Notice that we can apply Pythagoras theorem here again. This will tell us that 3x squared plus 5x squared equals to the hypotenuse 2y plus 8 whole thing squared. 3x squared plus 5x squared is 34x squared. And we know that x squared is equals to y plus 4, so let's replace that. Notice that the right hand side, we can also factorize out 2 squared, which is 4, and what's left over is y plus 4 squared. And we have a common factor of y plus 4 on both sides. Now, y plus 4 cannot be 0, otherwise y will be negative 4, and we do not like negative lengths. So let's cancel away the factor y plus 4. This tells us that y plus 4 is equals to 17 over 2. We want the length of BC, which is 2 times of y plus 4. So the answer will be 17. Now, question 9 looks pretty daunting, but trust me, it's actually quite easy. So let me go through it with it. Let n be a positive integer. Suppose that a1, a2, a3, so on is a sequence of numbers defined such that a1 is equals to square root of n plus 3 times n minus 1 plus 4. And the general term ak is equals to the square root of n plus 2k plus 1 times of the predecessor term ak minus 1 plus 4, where k is integers greater than or equals to 2. And we are told that a100 is 2024. Find the value of n. Pause the video here and give this question a good try. So what we can do here is we can first simplify a1. If we expand the quadratic n plus 3 times n minus 1, we're going to get n squared minus 2n minus 3. When you add 4, you're going to get plus 1. Notice you get a perfect square. So a1 is just n plus 1. So we can continue and work out a2. a2 is equals to the square root of n plus 2 times the k is 2, so 2 times 2 plus 1, so multiplied by the term a1 plus 4. So a1 is n plus 1, so let's sub that in. So we're going to get square root of n plus 5 times n plus 1 plus 4. Notice that when you expand it out, you get the quadratic n squared plus 6n plus 9, which is a perfect square. And when you square root that, you get n plus 3. And if you're going to continue this, you'll notice that a3 is n plus 5 and so on. So you're going to see a pattern. But let's see if we can prove that pattern. Of course, this is a competition and we are short of time. There is no need to prove the pattern. You can just assume that it's going to be plus 3, plus 5, plus 7, so on. But for the sake of completeness in this walkthrough, we're going to prove it. So the pattern that we want to guess is that AK is equals to n plus the 2k minus 1, which is some odd number, the doubling k and subtracting 1. How can we prove this? We're going to use the method of induction. So let's look, we'll assume that AK is true. AK is equals to n plus 2k minus 1, and we're going to consider what happens for the k plus 1 term. So that will be the square root of n plus 2k plus 3, because k is now k plus 1. So when we replace k with k plus 1, the first term inside the square root is n plus 2k plus 3. AK is 2n plus 2k minus 1, and you add 4. So if you expand this quadratic inside the third, you're going to get n squared plus 2 times of k, 2k plus 1 n plus 2k plus 1 squared. And this is a perfect square. So you are going to get square root of n plus 2k plus 1 squared, which will give you n plus 2k plus 1, which is exactly what we want. So this pattern is going to continue. So it's going to be n plus 5, n plus 7, n plus 9, all the way. By the time you reach A100, the 100th term, it will be n plus 199. And we are told that it's equals to 2024. Therefore, n must be 2024 minus 199, which is 1825, and that's our final answer. Question 10. Let n be the smallest positive integer such that the sum of its digits is 2024. What is the sum of the digits of the number n plus 2? Pause the video here and give this question a good try. So to make this n as small as possible, we would want the digits to be as big as possible so that there are less digits. So if all the digits are 9, that would be nice. Of course, 2024 is not divisible by 9. It has a remainder of 8. Therefore, n would be 8, 9, 9, 9, 9, 9, 9, and the number of 9s would be 224 9s in total. And if we add 2 to that, the number will be 9, 0, 0, 0, altogether 223 zeros with a 1 behind. So the digital sum of n plus 2 is just 10, and that's our final answer. Okay, question 11. If a and b are non-zero real numbers such that 1 over b minus 1 over a equals to 4, find the value of 3a plus 7ab minus 3b over a minus 3ab minus b. Pause the video here and give this question a good try. Again, this looks scary, but it's actually ridiculously easy. We'll take the equation that we are given, 1 over b minus 1 over a equals to 4. We'll make a common denominator on the left-hand side first, so we get a minus b over ab equals to 4. And then we'll just get a minus b to be equals to 4ab. Because you'll notice that in the expression that we're given, you can see that I can rewrite the numerator to 7ab plus 3 times of a minus b, and the denominator is minus 3ab plus a minus b. So we can sub away the a minus b and replace it with 4ab. This will give us 7ab plus 3 times of 4ab in the numerator, and in the denominator we have negative 3ab plus 4ab. So you have ab's on top, ab's below. You can cancel all the ab's. All you have left is 19. And that's our final answer. Question 12. If the 5-digit whole number 11ab6 is a perfect square, find the value of a plus b. Pause the video here and give this question a good try. Notice that 100 square is already equals to 10,000, so this number that we're looking at has to be bigger than 100 square. Notice also that the last digit is 6. Therefore, we're looking at 1x4 squared or 1x6 squared, because only 4 square and 6 square can produce a last digit of 6. So let's just guess and check. Let's guess 104 squared. Nope, it doesn't work. We guess 106 squared. Whoop, it works. Therefore, a plus b equals to 2 plus 3 equals to 5. And that's our final answer. Question 13, we are given n equals to 1 times 2 plus 2 times 3 plus 3 times 4, so on until 30 times 31. Find the value of n. Pause the video here and give this question a good try. So the trick here is we're going to split 1 times 2 to be equals to 1 squared plus 1. 2 times 3 is the same as 2 squared plus 2. 3 times 4 is equals to 3 squared plus 3, and so on and so forth until we reach 30 squared plus 30. So the sum of squares is given by the formula n over 6 times n plus 1 times 2n plus 1. So that would be this. And the sum of the natural numbers from 1 to 30 is just 30 times 31 over 2. This is just a computation. You calculate, you'll get 9,920 as the final answer. Question 14. Let x and y be non-zero real numbers where x is not equals to y if x squared plus root 3 of y equals to 4 and y squared plus root 3 of x equals to 4 also. Find the value of y over x squared plus x over y squared. Pause the video here and give this question a good try. So this question is rather tedious. I'm just going to give you the overview of this and you can work out the full details on your own. So we'll take the two equations and subtract them from one another. This will give us y squared minus x squared minus square root 3 of y minus x. And the 4's will cancel out, so it's equals to 0. So we have a difference of square which we can factorize. We'll get y minus x times y plus x minus square root 3 y minus x equals to 0. Since y is not equals to x, we can cancel out this common factor. So y plus x must be equals to square root of 3. This we can replace it back into the original equation x squared plus root 3y equals to 4. So this will give us a quadratic equation, x squared plus square root 3 times or square root 3 minus x equals to 4. And it's quite tedious to solve this, but you'll get the result of x equals to half of square root 3 plus square root 7. And when you sub this x value back into the earlier equation x plus y equals to root 3, you'll get the y value to be half of root 3 minus root 7. Of course, it's a quadratic. There's two possible answers. The other pair of answers is just x and y swapping the values. So there's no difference there. So here I've just shown you roughly the approach to get the value of x and y. Now the tedious part is to sub this back into y over x squared plus x over y squared. If you do it, you will be rewarded. The final answer will be 23, but it's just a lot of certs that you have to untangle. Question 15, the last question for this video. Find the sum of all two-digit even numbers n with the following property that n is a multiple of the product of its two digits. Pause the video here and give this question a good try. So we can brute force this. What you see here is a table of all the possible first digits 1 to 9 and all the possible second digits 2, 4, 6, 8, 0. I've included 0 even though it's not possible because the product will be 0 and there's no way you can get a multiple of 0. But anyway, if you just look through this entire table, you can identify the ones which are multiples. Notice that here 12 is a multiple of 2, 24 is a multiple of 8, and 36 is a multiple of 18. And if you check, there are no more such two-digit numbers. Therefore, the final answer is 12 plus 24 plus 36, and the final answer is 72. So that's my quick walkthrough of question 1 to 15 for this year's junior section round 1. Do stay tuned and subscribe to the channel for more Math Olympiad videos. If I have time, I'll make the solutions for the rest. Thank you for your kind attention and have a great day of learning.